Good afternoon, my name is Felipe Matamala. I'm currently researching in the Renewable Energy Laboratory of the Department of Chemical and Bioprocess Engineering and the Universidad Católica de Chile. For group research, the use of photosensitive surface to photoelectrocatalyze the hydrogen carrier production. So in this opportunity, I will talk about the synthesis of the surface bases on cuprate titanium oxide heterojunction on a transparent FTO electrode to be used in nitrate reduction. I would like to start by giving brief context on the nitrate problem. Nitrate reduction is an energetically and environmentally relevant topic for engineering because nitrate to natural conversion is the limited step for nitrate reduction reactions to obtain compounds of higher energetic value like ammonia, a molecule considered as an ion carrier. Today, nitrate can be tried or reduced by electrolysis and photocatalysis. It's possible to develop different processes and mechanisms depending on the conditions of the treatment or method used. But essentially, if we want to generate hydrogen carrier molecules from nitrate, we need to use an acidic medium to give the necessary proton for the reactions. If we want to use electrolysis for nitrate reduction, we will need large bias potential, and probably we need to use another metal like uranium as electrocatalysis. On the other hand, using a photocatalysis system is possible to perform this reduction with semiconductor as cadmium sulfate or other semiconductor reduction, but the most widely used semiconductor has been titanium oxide, used extensively to produce solar devices to derive power plants because it has a low cost, low toxicity, high chemical stability, and obviously commercially availability. Titanium oxide can absorb light radiation, generating a photoinduced electron hole pair. Then the photoinduced electron can jump from the conduction band to the valence band, leaving a hole behind. And this pair can participate then in reduction and oxidation reaction respectively. However, the energy required for this phenomenon to occur must be at least equivalent to the band gap energy of the semiconductor. So in the case of the titanium oxide, this is only possible when titanium oxide is exposed to the UV light, which is equivalent to 3 or 4% of the solar spectrum. Therefore, this process is not very efficient when we use solar light over titanium oxide. Although there are other semiconductors that can absorb radiant energy like titanium oxide, they don't have the same properties. But an intercell semiconductor can be complementary to the titanium oxide if the copper oxide one, also called cuprate. This is a p-type semiconductor that can carry out the reduction reaction that titanium dioxide cannot catalyze. And cuprate can absorb radiant energy equivalent to visible light. Also, is considered not toxic, and the synthesis is relatively low cost. Now, if we join both semiconductors to form heterojunction, now it's possible that the new system reacts to visible and UV light at the same time. Then, if we fix the heterojunction conductive and transparent glass like FTO, it's possible to generate a photoelectrode that follows the reduction on this surface. This is the general work plan for this research, and currently we are in this step, theoretical calculations. For first experimental step, the electrode synthesis, a colloidal titanium dioxide solution was deposited and spread on the FTO glass using spin coating. Then the FTO glass was sintered to generate the cohesion of the particles on the surface. And finally, an electrode deposit of cuprate was made using copper sulfate solution with a current intensity of the -1 milliampere. Here are images of physical appearance of the electrode synthesized with a geometrical area of cuprate deposit of 1 square centimeter and 28 square centimeter of deposit area to evaluate the field scalability of the methodology. Here we see scanning electron microscopy with field emission, and that was used for the electron surface analysis to rewrite an image of a cross-section to the surface, with which we determine the thickness of the deposit in around of 3 micrometers. Here we can observe the layer corresponding to the FTO, and over this layer, the titanium dioxide deposit. An element distribution analysis was performed for a cross-section of the electrode surface. So in this case, we observe the distribution of the copper atoms inside the titanium dioxide matrix. Then, to evaluate copper formation, we perform an X-ray diffraction analysis, where it can be observed the formation of cuprite and the absence of cupric oxide. This information is corroborated by Raman spectroscopy, where again the presence of cupric oxide is not observed in this area where the characteristic signal of cupric oxide was observed. Then the electrochemical behavior of the electrode was characterized using a cyclic potentiodynamic profile, where it's possible to see the difference of titanium dioxide here and how this is modified in percent of cuprite. There is the cyclic voltammogram from electrode with cuprite presence. On the other hand, diffuse reflectance analysis was performed obtaining the TiO₂ plot, where it's possible to analyze the interaction between both semiconductors. In this, observe that the titanium dioxide its band gap is similar to the theoretical values report in the blue line, and the red line, the presence of the cuprite is modified, showing negative shift to this band toward the blue spectrum, given the electronic rearrangement generated by the interaction with the cuprite. With Wachowski analyze, we study the p-type or n-type behavior of the semiconductor on the surface and flat back potential. If we compare the results, we can observe a positive slope from the titanium oxide relative n-type behavior. In this figure, we can observe a negative slope in the surface with cuprite, which is relative to p-type behavior, which will favor to perform the reduction reactions in the surface. When studying the photocurrent response, this is possible to observe how the electrode with titanium dioxide has an n-type behavior in the blue line, and how this is modified by incorporating the cuprite, changing this behavior towards a p-type surface in the red line. Finally, an analysis of the effect generated by the amount of copper in the electrode was carried out here, and it was observed that the electrodes with deposit of 10 minutes do not present a significant difference against the electrodes with 5 minutes of electrochemical deposition. Yeah. About the nitrate reduction, in this case, it was used a solution of sodium sulfate with a millimolar of sodium nitrite. The solution was stirred in the dark, and argon gas was injected during 40 minutes. The system was then illuminated with a xenon lamp with irradiance like a Wanson. In the figure 20, it's possible to see the photopoint response for this experiment. There. The result for the conversion of the nitrite to nitrite was measured by Grace Richmond and are present in the figure 21. The results were get after 3 hours of the photoelectrocatalysis. When we working with potential more negative at minus 0.6 volts, the formation of metallic copper on the surface was detected, and then the system stopped responding to the illumination and becomes an electrochemical system, obtaining high and better conversion arrays. We confirm this behavior when we study the X-ray patterns, and we observe when I work in minus 1 volt, the Kubrick patterns are lost here, and metallic cover patterns emerge there. The main conclusion of brief study were this is possible to form the heterojunction on FTO glass according to the process synthesis. The result of photoelectrochemical characterization show that the electrode responds to the light with a p-type semiconductor behavior, promoting reduction reaction in the surface. This is possible to perform the photoelectrocatalysis conversion of the nitride to nitride with lower potential complement by illumination. The next step of the research are study the formation of the products like ammonia or nitrogen, especially ammonia, like hydrogen carrier molecule, and evaluate the use of the theory semiconductor to improve the corrosion stability, and then use solutions with less pH values, and use theoretical calculation and molecular dynamics to study the mechanism for heterojunction and product formation. Here, for example, we represent the molecular dynamics simulation to the formation of cuprate molecules on titanium or titanium oxide nanoparticles. My acknowledgement to my friends and colleagues from the research group of Professor Cesar Saez in the Department of Chemical and Bioprocess Engineering, and to research group of the Professor Mauricio Isaacs in the Department of Inorganic Chemistry. The acknowledgement to Anit Konicit for the doctoral grant, Fondesit and Fondetip for the corresponding funds, and to Research Center of Nanotechnology and Advanced Materials, and finally to the RC Center of Excellence for Electromaterials Science of the University of Monash. And thank you for your attention.